Hey everyone! So we are moving on to a new chapter, chapter 14, which is equilibrium. So now we're not just dealing with reactions that go one way, we're dealing with reactions that can go forward and backwards. And the first thing I want you to realize is that when I say equilibrium, equilibrium means when the rate of the forward reaction is equal to the rate of the reverse reaction. Sometimes we might see this as saying that equilibrium is we have the same amount of reactants and the same amount of products. This is not the case. Equilibrium is just when it's done making products or done using up reactants. So sometimes we could have a whole lot of reactants and a little bit of products. Sometimes we could have a whole lot of products, a little bit of reactants, and sometimes we can have equal amounts of reactants and products. But equilibrium, think of it as just shifting one way or another of a reaction. So you are now going to start seeing reactions that have these double arrows. And that just means that now we have reactions that could go forwards and backwards. They can start to create some products, but then we might change the conditions a little bit and they might shift back to reactants, which is actually how a good amount of reactions actually happen. So today we're going to introduce you to equilibrium. We're going to be doing some equilibrium expressions. We're going to learn about equilibrium constant K, and we're going to get a good understanding of how we kind of see how reactions react due to equilibrium in the real world. Okay. First thing we got to realize is we got to realize that there's this thing called the equilibrium constant K. So let's go ahead and let's write down equilibrium constant K. Alright, and you might see this written as K, KEQ, which is just K equilibrium. You'll see it as KC, which is K concentration. You'll see it as KP, which is K pressure, and then when we get into acids and bases, you'll also see Ka and Kb as well. But right now, let's just focus on these four for today. And what you need to know is that when K is greater than 1, so I'm talking like 2, 3, 1 times 10 to the 5, 1 times 10 to the 10, 1 times 10 to the 15, that means you're going to have more products produced. Okay, so when a reaction happens, if the equilibrium constant K is greater than 1, you're going to have a lot more products produced. If K is less than 1, I'm talking 0.99, 0.5, 1 times 10 to the negative 5th, 1 times 10 to the negative 10th, you're going to have more reactants. Okay, so that means the reaction isn't really going to happen. You're just going to have a whole lot of reactants just there. And a reaction isn't really going to occur. It's not going to create too many products. And then, of course, if K equals 1, that just means the products and reactants equal one another. So you're going to have the same amount of products as you will reactants. Get this concept into your brain real well, because this is the foundation of acid bases. It's a good foundation. Equilibrium. Okay, know what these equilibrium expressions mean. Know that 1 that is greater than 1 means you're going to have a lot of products and not a lot of reactants left over. Same with K to the minus 1. Make sure you know if you see a really small K that you're not going to have a whole lot of products being produced. With K that is greater than 1, if we have a huge Ka that is greater than 1, we have a really strong acid. If we have a K that is really less than 1, we have a really weak acid. Okay, K equals to 1. We just have a reaction that only happens kind of halfway. Okay, be aware of that. Be aware of these Ks. Alright, now let's talk about some more of these equilibrium expressions that we've talked about. So now what we're doing is learn how to write equilibrium expressions. So with kinetics, back in our last chapter, we just focused on the reactants, right? They're the only thing that affects the speed is what's in the reactants. But now with equilibrium, since the reaction could go forward and backward, we have to include the products now. So now our products are going to affect our speed of our reaction, or how much we produce and how much we don't produce. So how do we do this? So equilibrium expression, which is given as K, is going to equal our products over reactants. It's going to equal the concentration or pressure of our products over the concentration of our reactants. So now we are doing products over reactants for our equilibrium expressions. And these little numbers in front, those are going to be our coefficients. If our products or reactants have a coefficient in front of them, we put them as an exponent. So if this was a 2, we would put a 2 as our exponent. If this was a 3, we would put a 3 as our exponent. And if these were numbers, we would put them as exponents as well. So what we're going to be doing later on is I'm going to be giving you concentrations, and we're going to be plugging this in to this equilibrium expression. We'll solve for it, and then we'll get a K. And that number, if it's greater than 1, will tell us that we'll have a bunch of products produced. If we get a K that's less than 1, it's going to tell us that a lot of reactants are still left over after the reaction. So that's what we are going to be doing for the majority of this chapter. We are going to be figuring out, given a certain amount of concentrations, how much reactant is going to be left over or how much product is going to be produced from these equations. One thing to mention with these equilibrium expressions, these concentrations here, this could be, CH4, this could be O2, this could be H2O, and that could be CO2. We only include reactants and products that are in the gaseous or aqueous form in our equilibrium expression. Okay, so we only include gaseous and aqueous states. Okay, so when we're writing our equilibrium expression, if we see this as a solid, we're not going to include that product. If we see an aqueous, we will include that in our product. Okay? Same with a gas, we'll include it. And if you have a liquid, you won't include it. That's just because solids and liquids have too strong of intermolecular forces that they're not going to affect the reaction too much. Okay? Only those things that are really spread out, like aqueous solutions, and gaseous compounds are going to be able to affect equilibrium. So be aware of that. So let's do a couple of examples here where we're going to be making our equilibrium constant expressions. All right, so I want you to write the equilibrium expression for this reaction right here. So again, this is equilibrium. So we're going to be including products and reactants. If I was doing kinetics, I'd just care about the reactants. But again, equilibrium includes both. So remember, our equilibrium expression is K equals products over reactants. And remember, we only include states that are in the gaseous or aqueous state. So let's go ahead and start with our products on top. So it looks like we have NO2 in a gaseous state and H2O in a gaseous state. So we're going to include both of those guys. So let's go ahead and put NO2 and H2O. And then remember, these coefficients we got to treat as exponents. So NO2 exponent is going to be 4. H2O's exponent is going to be 6. Now let's go ahead and put the reactants on bottom if they're gaseous or aqueous. Okay, they're both gaseous and aqueous. So let's go ahead and let's put those on bottom. I got NH3. It'll be to the 4th. And I got O2, and it'll be to the 7th. Right? So that's our equilibrium expression. That is it. Let's do a couple more of these. All right, so here I'm asking you to write the Kc and Kp expression for N2O4 to 2NO2. Kc and Kp, that's just the same thing as equilibrium expression, except one is going to be put in terms of concentration. That's what Kc stands for, which is what we did in our last example. And one's going to be put in terms of pressure, which just changes up how it looks a little bit. And I'll explain that here in a second. So let's go ahead and do Kc, since that's pretty standard for what we usually do. We'll do Kc. And we are going to do products over reactants once again. And again, only include those gaseous and aqueous states. Here, they're both gaseous. so we're going to include them. So again, Kc is concentration, which is the standard for how these equilibrium expressions are written, but I'll just put it in square brackets to show that it's in concentration as usual, and put it to the second. And then I'm going to do the same for N2O4. No coefficient needed because there's a 1 in front of it. Alright, so that's Kc. It's just the standard way we've been doing it, the C relating to the concentration, which we have been doing. But now Kp is in terms of pressure, so we could solve for K using concentration or pressure. Be ready for that, because on the AP exam they'll throw a pressure problem at you, trying to catch you off guard, but it's the same thing as concentration. So, I'm going to put Kp, and then instead of square brackets, all I do is I just put P subscript NO2. That just stands for the pressure of NO2, and once again, I will square that, just like I would my concentration. And then the bottom is the same as well. It's going to be P N2O4, but once again, no coefficient needed. So, be ready for a Kc or a Kp expression. They're both the same, it's just this one deals with concentration and that one deals with pressure. So last one here, I just want the Kc expression for this reaction. Here I can't really do a Kp expression because these guys aren't in gaseous form, right? Pressure is just based off of gas. So here I can't use these ones. So let's just go ahead and write this. Again, I could ask for the equilibrium expression or the Kc expression. Either one. They're the same thing. So here it's products over reactants. So my products are Ag plus and Cl minus. No need for coefficients because they don't have any. Over reactants. Can I use AgCl? No, it is a solid. It does not affect the equilibrium at all, okay, because it's in solid state. So here is my equilibrium expression right here. No need for anything on bottom because that guy's a solid. He does not affect equilibrium. All right, so let's move on to the next thing, where what would happen if I flipped or halved these reactions? How would that affect the equilibrium constant K? All right, everybody, so here I have that same reaction we were just looking at. It's silver chloride, and it is dissolving or dissociating into Ag plus and Cl minus. And here I've given you actually the equilibrium expression of Kc, which is 1.8 times 10 to the negative 10th. Now, before I talk about reversing this or doubling it or anything like that, let's look at that K. That K is 1.8 times 10 to the negative 10th. So do you think that we're going to have a lot of reactants, or do you think we're going to have a lot of products? Well, when I look at this thing, I look at my K, it is a lot less than 1. That is 1.8 times 10 to the negative 10th. That's 0.0000000000018. That is an extremely small K. That's a lot less than 1. So we're not actually going to have a whole lot of products here. So if I were to ask you, does AgCl dissolve really well? You would tell me no. Okay? Its Kc is super small. That means it's not going to dissolve very well. It's not going to create a lot of that Ag plus and Cl minus. Alright, so think about that when you're seeing these Kcs. What are they telling us? Alright? So right now that's really, really small. But let's say I were to reverse this reaction. Say now the reaction is Ag plus Aq plus Cl minus Aq. And now it's going to AgCl solid. What is my new Kc going to be? What is my new equilibrium constant going to be? Well, whenever we reverse a reaction, our new Kc is going to be 1 over our original Kc. So in order for us to figure out our new equilibrium constant K, all we're going to do is, since we reversed this reaction, we're going to put 1 over our original Kc of 1.8 times 10 to the negative 10. And that will tell you that what we will have for our equilibrium expression. So I'm going to go ahead and plug in 1 divided by 1.8, second e to the negative 10th. And now I'm going to get a new K of roughly 5.6 times 10 to the 9th. No units on these, okay? So that is my new K now that I've reversed this reaction. And that makes sense, right? Because if I have a reaction that's reversed, originally, you're going to have a lot of reactant because that Kc is so small. But if I reverse it, you should expect now that there will be a lot of product produced because Ag plus and Cl minus are going to want to form that solid. It doesn't dissolve very well, okay? So when we flip a reaction, 1 over Kc. Now, what if I were to do something like this instead, where I double everything, okay? Some of you might be saying, just times your Kc by 2. No, we don't do that, okay? What we do is if we double everything in our reaction, we take Kc squared, all right? So that's what we're going to do. We're going to take 1.8 times 10 to the negative 10th and square it, and that'll give us our new Kc, okay? So I'm going to do 1.8 second e to the negative 10th to the second, and now our new equilibrium expression is 3.24 times 10 to the negative 20th. So now it's not going to dissolve very much at all. Pretty much just because you saturated the solution so much, right? If you want something to dissolve, you want as little of a substance in there and a lot of water as possible because then that water can dissolve it. Well, if you add double the silver chloride, okay, you're saturating a lot, it's not going to want to dissolve anymore, okay? There's more AgCl there that it could kind of bond to be stronger to. So again, if we flip it, it's 1 over Kc. If we double it, it's Kc to the squared. What if we halved it? Well, you could probably figure this out, right? If we doubled it, we squared it, okay? We took it to the exponent of 2. But if we half of it, we're going to now square root our original Kc. So now we'll go ahead, I'll take the square root of 1.8 times 10 to the negative 10th. And now, our new Kc is 1.34 times 10 to the negative. All right, so be aware of that. We double the expression, or we put 2 coefficients in front, we square it, we half the coefficients, we square root it. If we flip it, we do the quotient of it, the 1 over Kc. All right, now let's go ahead and let's do some examples where we actually have some concentrations and we get to solve Kc for ourselves. All right, everybody, so some questions that you'll be seeing is if I'll give you a certain reaction and at equilibrium, I'll give you a couple of concentrations and I want you to calculate K. So I want you to calculate that K so you could tell me if this produced a lot more products or if this produced a lot more reactants. So let's go ahead and let's start figuring this out. If we ever want to solve for K, the first thing we got to have is our equilibrium expression, which our equilibrium expression is our products over our reactants. So let's go ahead and do that real quick. So I have K equals products. Is this a gas? Yep. So I'm using it. I'm going to put NH3 and I'm going to square it because of the 2 in front. Now I'm going to put the reactants on bottom. They're both gases, so I'm including both of those guys. Got N2 gas, and I got H2 gas, but I'm going to put it to the third. So now I got my equilibrium expression. Easy stuff. But now I want to calculate my K. So now it's pretty easy. All I'm going to do is plug in these concentrations. Once I plug in those concentrations, it'll give me a K, and then I could tell you if it's product favored or reactant favored. So let's go ahead and do that. NH3 is in there, so we're going to put 3.1 times 10 to the negative second squared. Now we'll put N2 in there, which is 8.5 times 10 to the negative 1. And then let's put H2 in there, which is 3.1 times 10 to the negative third. Don't forget to cube it. We do that every now and then. We forget to do that. I plug this into my calculator and I should get an answer of 3.8 times 10 to the fourth. That is my K value. So now I'm going to ask you, is this product favored or is this reactant favored? And you should say product favored. This K is a lot greater than 1, so that means we're going to have a lot more NH3. This is a favorable reaction. It likes to react and give us a lot of product. Right? Let's do another one, but this time with pressure. So here is our next example, but now we're using pressure. And I just kind of want you to think about why we can use concentration and pressure. Concentration, right, it makes sense because we increase the concentrations, we got more molecules in there. Pressure, how do we increase pressure? We add more molecules, okay? So the higher the pressure, we've added more molecules and we've also created a greater reaction. So that's why we're able to use concentration or pressure for these equilibrium expressions or equilibrium calculations. So once again, I want K. I just put at 25 degrees Celsius. It's good to know that it's at a constant temperature. And it's at equilibrium. That's good to know too, because later on we'll be doing some calculations where it's not at equilibrium. And now let's go ahead and let's solve for K. Well, once again, I need an equilibrium expression to help me out here. So I'm going to do K, and this time I'm just going to put Kp because I'm dealing with pressure. And my equilibrium expression now is going to be products over reactants. Remember that for pressures, we do P subscript NOCl, and I will square it. And this is all good because that's a gas. If that was a solid or a liquid, I couldn't use it. Bottom, all right, reactants. These are both gases. I'll put P NO squared and PCl2, not squared because there's not 2 in front of it. And now I'm just plugging and chugging, okay? So I'm going to go ahead and equal this, and I'm going to plug in my pressure of NOCl, which is 1.2. I will square that. On the bottom, I will put 5.0 times 10 to the negative 2, and I will also square that. And then Cl is just 3.0 times 10 to the negative 4. Right, so I've plugged everything in. I'm going to calculate this one, and I calculated this previously, and it is 1920 is my Kp. And then I will ask you, is this product favored or reactant favored? It is product favored. Greater than 1, so that means we got more products. All right. Remember, if I were to just go ahead, say I were just to go ahead and change these coefficients by half and reduce everything by 1. All I would have to do is square root this Kp, right? All I would have to do is square root 1920 to get my new Kp of 43.8. Alright, so remember, I might be asking you questions like that to solve this, and then I might change up the coefficients and you'll be like, oh man, I gotta write a whole new K expression. No, just square root your Kp. Alright, so that is our intro to equilibrium. Things will get a lot tougher, but this is a good intro. Make sure that you just know how to write those equilibrium expressions. Know for sure how to understand K. That a high K means lots of products and a low K means lots of reactants. Alright, and make sure you know how to flip those reactants and how to solve for a new equilibrium constant K. Please reach out if you have any questions, and have yourselves a great day.